Excellent. Hello again, and I'm going to get started now. My name is Iqbal Khan. I'm a technology evangelist at Alachisoft. And today we're going to talk about how to scale .NET applications in Microsoft Azure. I'll try to keep it as interactive as possible so that as I'm talking, if you guys have any questions, just ask me, and then I'll be able to answer it right at that time. Just give me 1 sec. Some of it is going to seem a little basic to you guys, but I'm going to do it anyway for completeness purposes. So we'll start with a couple of definitions. What is scalability? Scalability is essentially high application performance under peak loads. So if whatever your application performance is with 10 users, if you can get the same with 10,000 users, you probably have a scalable application. So that's the basic definition of scalability. What is linear scalability? It is if you add more servers to your infrastructure, and these could be your web servers, your application servers, your transaction capacity, your capacity to handle more and more users should also increase in a linear fashion. As compared to a non-linear scalability, where initially, as you add more servers, your performance increases, but as you can see, it's increasing at a decreasing rate. So it's a slope that is going this way. At some point, it's going to peak, and then if you add more, it's going to actually slow down. It may even crash. So if you add more load, it's going to crash. So if that's what you're facing, which is what most applications face, then you have a non-linear scalability. That means you cannot solve this problem by adding more web servers or more apps servers to your mix. Which applications need scalability? These are the most common are web applications, ASP.NET applications. If you're a .NET developer, these could be web services applications. Web services are also the back end for the Internet of Things, which is the new terminology where you have a lot of mobile devices that are connected to the Internet. They all have to talk to some back end, and that back end is usually some sort of web services, which is, again, a scalable environment. These could also be big data analytics. So if you're a large company and you have a lot of data to process, that data has to be processed in a distributed fashion, so that is also a place where you need to scale big time. Or any other server applications that you might have, which just needs to process a lot of requests. So I just want to set that parameter in terms of what are the types of applications that fall into this category. If you're doing a desktop application or a mobile client application, this type of issue does not apply to you because you don't have a lot of users. Even if you do, it's the back end that's going to have problems. So what is the problem? The problem is that the application tier, this is not the problem that the application tier scales linearly. You can add more servers, as we said, to your web application. It's a load balanced environment. As you add more servers, you can handle more and more requests by the users. So that scales very, very linearly, but data storage becomes the bottleneck. Data storage is usually relational databases or mainframe data or any other traditional data store that you have. And I don't mean the NoSQL that I'll talk about in a bit. So, and because this becomes the bottleneck, it doesn't really matter whether this can scale or not. You don't have linear scalability because if you go back to this diagram, you're going to add more and more servers to your application tier, but you'll see this decreasing curve. Why? Because the back end, the data storage, is not able to handle. So it's becoming slower and slower and slower until it crashes. Here's another way to look at this picture. Let's say if you were in Microsoft Azure, you would have a virtual network, and let's say you have an ASP.NET application or WCF application running. You have some sort of a load balancer here, and as we said, you can add more servers here, but these are the different types of data storage that will become the bottleneck. One is your relational database, which could be SQL or Oracle. It doesn't matter which database you have. If it's a relational database, it's going to have problems. Similarly, for ASP.NET, the ASP.NET sessions have to be stored somewhere. And in Azure, they are stored in SQL database. So they fall into the same category. If you have any on-premise data, that also falls into the same thing. Even if you have a mainframe as your legacy data, a mainframe can scale up, but it cannot scale out the same way. But if you have a NoSQL database, that usually does not have a scalability problem. So if you look at this picture, it almost seems tempting to say, well, why don't we just use NoSQL as the answer? But can we replace NoSQL? In most cases, we can only replace it with a small subset of the data set, which is unstructured, which is your textual data, your social media, whatever the new data types are. The traditional business data is all relational. It's going to stay that way, and for good reasons. So you have to live with a relational databases. You have to live with the legacy mainframe. So NoSQL, although it's a great technology, it has a specialized need or has a specialized use, which does not replace relational databases. So if you're thinking about fixing your scalability problems by removing your relational databases, I think for most of you that is not going to be possible. For some of you that might be, and for many it would be that a subset of the data can be moved to the NoSQL database, but still, the problem persists. So that is where, if you have an in-memory distributed cache, the benefit of that is that you can use it with a relational database. It does not ask you to replace relational databases with this as the storage. It is not a permanent storage. It's an in-memory store. It's temporary in nature. It is faster and more scalable than the traditional databases. It's actually faster than even the NoSQL database. It's all in memory, and it's very close to your application than the NoSQL database would be. On the Java side, the in-memory distributed cache is called in-memory data grid. But it's the same thing, essentially. On the Microsoft side, the word distributed cache has become more popular. So that's why I've used that term. So what is an in-memory distributed cache? It is that you have that same application tier which scales very nicely, and the same database tier that does not scale. You put an in-memory distributed cache cluster in between these two layers. And this is only a logical thing. It does not mean that these are separate servers. These could be the same servers as your application, but logically they are between the application and the database. And this scales, because it's a distributed cache, it's a key value store, it scales in the same fashion as the application tier. So because it scales in a linear fashion like the application tier, the database is no longer the bottleneck. And the reason is because about 70 to 90% of your normal database traffic is going to be diverted to the in-memory distributed cache. And I'll talk about why that is. There are some misperceptions about what you should cache and what you shouldn't. Most people think that you should only cache static read-only data, whereas the real gain comes from caching pretty much everything. So an in-memory distributed cache has in-memory store, so it just has lots of memory. The most typical configuration would be 16 gig of RAM in each box, dual CPU, quad-core type of a box. Not a very high-end configuration. 64-bit because...
That would be the VMs, right?
Yeah, in Azure, these would be the VMs. So you would have a minimum of 8. I mean, you could either 4 to 8 virtual cores would be your minimum. Ideally 8 and minimum of 4. And some people would have even 16 virtual cores. And then just lots of memory. And the more memory you have, the more processing power you need, because garbage collection and all the other things need to process much more data, so it needs to have more CPU. But these are essentially low-cost boxes. Unlike your database, which is a high-end server, these are typical web server type of a configuration boxes. And there's a cluster of them. And that cluster means that the cluster pulls the memory and CPU together into one logical resource. So that the more servers you have, the more memory you have, the more CPU processing you have, and all so on and so forth. If you're using a distributed cache, these are the first question that comes to mind is, well, what is the type of performance and scalability should I expect from a half-decent distributed cache? Now, not all caches have the same performance, so that's why I'm keeping sort of the expectation on what you should see. So if you have a 2-node cache cluster, you will see around 32,000 reads per second and 50,000 writes per second. These are 1K objects. These are going across the network, but to a local subnet. But it's all in memory. There's a key, which is a string, usually about 32 character string. But of course, in reality, if you do the 64-bit math and all of that stuff, it's more than a few hundred bytes of string, and then 1K is the object size. So, that would be a standard kind of a benchmark that you should expect. And when you go from 2 to 3, it scales in a linear fashion, although the writes are not as fast as the reads are, because of some of the reasons are that there's some replication that needs to happen. But it's still a straight line: 32,000, 48,000, 64,000, 80,000, 96,000, 50, 72, 96, 120, 144. So as you can see, these are numbers that if you had to achieve through your database, you would need some pretty strong hardware. And even then, it would max out, and then you can't go any further. Whereas here, you can keep going. You can build a cluster of, the most typical clusters are 2 or 3 server clusters, because for most people, especially in web applications or web services, 2 or 3 server cache clusters are, so you can say 32 to 50, between 30 to 50,000 writes and 50 to 70,000 reads per second is a pretty decent capacity. Now, if you have 2 or 3 servers here, it doesn't mean that you have 2 or 3 servers in your application tier. Usually, there's a 4-to-1 or 5-to-1 ratio. So for every 1 server, you have 4 or 5 web servers. Of course, a minimum of 2 cache servers for redundancy purposes. So if you have a 3-server cluster, you have anywhere from 12 to 15 servers in your application tier, which is pretty decent size. Most companies, their application tier has less than 20 servers. There are very few companies that have more than 20. And again, I'm talking about the web and the web services type of applications. Big data is a different beast. You might have more, depending on how much. But that's the type of performance that you should expect from a half-decent distributed cache. Okay, so what are the ways that you can use a distributed cache? There are three most common ways that you use it. And again, I'm talking from a .NET perspective here. The first is application data caching. Application data is data that lives in your relational database, your mainframe, whatever your main application database is. So that is what I call permanent data. That data has to be persisted permanently. So when you cache it, the data exists in two places, the database and the cache. So all the issues of having data exist in two places have to be resolved by a distributed cache if it's a good cache. If it's not a good cache, then you will have to resolve them yourself. The second use case is some ASP.NET specific data, which is transient data or temporary data. Transient data is data that gets created at runtime. For example, ASP.NET sessions is transient data. It gets created when you log in or you access a web application first time, and it goes away after 20 minutes of inactivity. View state is another case, and there may be also other transient data that your application itself is generating. So that's the second common use case, and I'll go into more detail with each of these. I'm just giving a high-level picture at this time. The third common use case is something that a lot of people don't know, which is runtime data sharing through events. You've probably heard PubSub, publish subscribe model, that you can use. So that's the type of model that you can use here. With the help of events, you can do a PubSub type of data sharing, and that's also transient data. That may be permanent data, but that it might exist in the database. But from a sharing perspective, it's transient. That once you've shared it, it no longer needs to be kept there. It just needs to be taken out. But it's also most of the time created at runtime. So those are the three common uses of a distributed cache. So let's now talk about what does a distributed cache look like, what are its pieces, what is a typical architecture. So there are four different goals or things that a distributed cache architecture tries to achieve. Again, high level. Number one, and the most important, is high availability. Because a distributed cache lives in your data center, it is like your database. And if it goes down, your application could go down, especially if you have this transient use. I mean, in case of application data caching, you still have the database to go back to. You'll take a performance hit, but the application will keep running, although you don't want to take that hit, because the whole reason you're using this cache is so that you can handle that peak loads, which if the cache goes away, the peak loads are also going to become a major problem. So high availability is very, very critical. So any distributed cache that is half decent should address this. Number two is linear scalability. The whole reason you're using a distributed cache is this one. So if you can't do that, then there's no use even using a distributed cache. Number three is the data replication, and this you need because it's an in-memory store. Anytime you have an in-memory store, memory is volatile. If you turn off the computer, if it crashes, you lose that data, which you may not want to. And again, I'll go back to this picture. Permanent data, you can afford to lose and then refetch from the database, but you don't want to, because you might have populated 30, 40 gig of data in the cache, 50 gig of data in the cache, and to repopulate that is a major performance hit. And because if this happens under peak loads, the whole reason you do all these things is to be prepared for the worst case. Because the worst case is so costly to your business that you cannot afford for something to go down. Even though under non-peak hours, you might think it's an overkill. You have extra hardware, you have extra everything, but it's the peak hours that define everything. So data replication. Fourth is a feature called client cache, which is that it's also called near cache, and I'll explain that in a bit. Any questions so far? Okay. So what is a typical, before I even go and address those four aspects, let's see what are the different components of a distributed cache as a software packaging. So there's a client API and library. Most distributed caches have an API that you write to. It's a pretty simple API, and I'll show you this API. It's a pretty simple API. It's cache.insert, cache.add, cache.remove, and there's a key. Key is usually a string, and then the value is an object. And the value could be any .NET object. And because there's an API, so there's also a library, some .NET assemblies that get installed on your web or application server box. And then there's a cache server component that we talked about, and the cache servers talk to each other on a TCP protocol. And the client, the cache client, which is your application, talks to the cache through that client library, also most likely using a TCP connection. These are just simple socket stuff. And there's some server-side code that you write that resides on the cache servers, on the cache cluster. And that is your read-through, write-through, cache loader, and a bunch of other code. So those are the pieces of a distributed cache that you should keep in mind. Anytime you have questions, please do stop me. Okay, so the high availability, how does a distributed cache achieve that? It achieves it by having a dynamic cluster in nature. So it's if it has a peer-to-peer cluster, it's dynamic. If it's a master-slave type of a cluster, it's not dynamic. Because a master-slave, if the master goes down, you're hosed. Everything either stops working or becomes read-only or whatever. But a peer-to-peer architecture means that every server in the cluster is a peer. Any server can go down, which of course anyone can, right? So, and it does not stop the cache. If that is the architecture of the cache, then it has a peer-to-peer architecture. So that's the first aspect of the architecture that achieves high availability. The second aspect is connection failover. If any server goes down, well, the connection failover is two parts. One, within the cluster itself, if any server goes down, the other servers are self-healing. So the word self-healing means that they automatically readjust to the new reality. So they will change the cluster membership information. They'll move data around if they have to. Whatever they have to do, they'll do to make sure that they can go from a 3 server to a 2 server, or from 5 to 4, or so that's the first part. The second part is the cache clients, which is your applications. They also have to continue working. So the cache clients are talking to one or more cache servers. That depends on what the nature of the cache is, what we call caching topologies. But if, let's say, if some of the clients are connected to one of the server and that server goes down, the clients should have the ability to continue working without any interruption. And that is not your application code. I'm not talking about your application. I'm talking about that client library should have that logic built into it, that it automatically connects to other servers and continues working. So all the operations are smooth. So that's the second aspect of a distributed cache, very important. The third is dynamic configuration, which is that if you want to be able to add servers at runtime or drop servers at runtime, the only way you can do that is if all the configuration information is propagated within the cluster and also to the cache clients at runtime. If you don't, go ahead.
If that server goes down, the data that's cached is also gone, and after that the application will just say there's no items cached and it will receive the data from wherever that data is from. Or there is some kind of replication in data. So if one server goes down, that cache data can be found on other servers.
Yeah. Very good point. I'm going to go to that on the next slide. I'm not even talking about the data yet. I'm saying that if the client doesn't even have the ability to say, okay, my server has gone down, I need to connect to another one. Let me give you an example of this. For example, if you take Memcache, I'm sure you guys have heard of Memcache. Memcache does not have any dynamic. The built-in Memcache, the standard official Memcache. So if a cache server goes down, the client does not have the ability to automatically connect to other servers. Now, there are some third-party solutions that try to provide that ability, but the built-in Memcache doesn't. That's what I mean by connection failover, is that the software, the cache should itself know that if a server goes down, everything should continue working. Now, data loss is your choice. If you turn off replication, then even though the application will continue working, it'll lose some data, but nothing stops. It'll get the data from the database, if that is your business need. But if it doesn't even continue working, because one server goes down means that application is hosed. It's going to keep trying to talk to that box, and that box isn't there. That means that the failover is not supported, or to recover from the failover is not. And the same way, dynamic configuration is, that if you don't propagate information at runtime, you can't add or remove servers at runtime. How are you going to add a server if the clients have to hard code everything? I mean, again, keep in mind, 100% uptime means 100% uptime. You can't stop things. You can bring some of the boxes down, but you can't bring the entire application down, and you can't stop the entire cache. So that's why dynamic configuration. So that ability to add or remove servers at runtime without stopping anything. Okay, now the other part, and that's the part that you talked about, is replication and what else. So caching topologies is a term that determines how the data is structured, where is it stored, how the clients connect to the cache, which servers they connect to. So again, distributed cache should provide partitioning. If it doesn't provide partitioning with replication, then it's not going to address the needs that we talked about, those four goals. So partitioning means that the entire cache is partitioned. So typically the way it works is, these are buckets. So you might have 1,000 buckets, and every server contains 1/n the number of buckets. So technically you could have 1,000 servers and no more, right? But most people, almost nobody has 1,000 cache nodes. So every partition has multiple buckets. And that information about which partition has which buckets and which bucket is mapped to which key value range is what I'm calling a distribution map. Distribution map is information that has to be propagated to the clients. Or at the minimum, it has to be propagated within the cluster. So let's say if you wanted item number 1, which is right here, what if you came to this partition and says, please give me item number 1? Now, it doesn't have it, right? It has item number 3 and 4. So there are one of two things it can do. It can either say, sorry, don't have it, or it can go and get it from partition 1 and give it to you. Again, it should go and get it, because your application should not have to worry about the weaknesses of the cache. The cache should take care of things. Now, ideally, you should go straight to partition 1 and get it, because so that you don't want to take this extra hop. So that is if you have the distribution map propagated to all the cache clients, and then the cache client uses that distribution map to connect to every server. Connecting to every server means it knows that if it wants item number 1, it's going to go straight to partition 1. If it wants item number 3, it's going to go straight to partition 3. And so that's the first part of partitioning. That partitioning should give the cache clients the ability to know where the data should be. The distribution map does not contain every key. It just contains ranges. That this range is mapped to this bucket, which is in partition 1. This range maps to this bucket, which is in partition 2. That's the first part. Second part is, again, let's bring this dynamic configuration back into this picture. That what if you were to drop server 3? It crashes, or you need to just bring it down. That means partition 3 is no more. Partition 3 goes away. Let's say there's a replica of partition 3 right here. You guys can see this, right? Okay. But now you have 2 cache servers and 3 partitions, which is not right. I mean, it should be the number of servers equals number of partitions. So partition 3, which used to be replica 3, needs to go away. It needs to merge itself with the existing partition. So it's going to give some of its data to partition 1, some of its data to partition 2. Again, all at runtime. It needs to do that for high availability. If it doesn't do that, then the cache is not highly available.
If each partition has some range, and partition 3 has third range, right? For example, A to K to
Right.
U, and then U to Z.
Right.
So that U to Z should stay, partition 3 should stay, partition 1 should stay, and the middle partition should be split into the partition 1 and 3. That's the way how it works? Or
Well, each
some nice logic, so it's not
each product will do it in its own way, but from your perspective, it should handle the fact that partition 3 cannot exist. I mean, there can only be 2 partitions left. Now, how the data is merged, I can tell you that in case of NCache, the buckets are actually moved, because the mapping of hash value is not to partition, it's to bucket. So, and you have 1,000 buckets. So the buckets of replica 3, half of them will go to partition 1, half of them go to partition 2, and that way it's good. But another distributed cache will do it another way. But from your perspective, they need to be able to handle this movement of data at runtime. If they can't handle it, that means you don't have high availability. So partition 3 goes away, and then a new replica of partition 2 has to be created here. So all of that should be done at runtime. Now, this is different from a NoSQL database. I'm assuming that you guys are familiar with the NoSQL database space. In a case of a NoSQL, you're talking about data on the disk database, and the size of that data is much bigger than an in-memory distributed cache. So there, you cannot just move partitions on the whim. What if server 3 went down just for 10 minutes, and it's going to come back, and the data that you had is in terabytes? You don't want to move everything from server the replica 3 to others. So you would take a different strategy. You would wait and maybe make some of the data read only, or something of that nature. Maybe you would stop having the replica for a brief period of time. Maybe you'll want the database admin to intervene and choose what really happened, because you don't know whether that server went down for a brief period of time or whether it's down permanently. Maybe it's just hosed. So, but in case of an in-memory distributed cache, the nature of the beast is different. Even though it looks similar, but the most prudent thing to do is to immediately move data. Because if you don't move it, you have problems. Because that memory is gone. The other box, even if it comes back up, it's not going to have that memory. So there's partitioning, and again, I'm trying to go deep into this so that you guys get a sense of the complexity involved in this. And then there has to be replication. Most of this replication is asynchronous. Most common practice is to do it asynchronous, but a good distributed cache should provide synchronous replication also, because some data is just too sensitive to be left for asynchronous replication. What if you have a corporate bank wire application and you're some large bank and every cached item is potentially $1 million worth of bank transfer. So you don't want to leave that $1 million on an async queue, right? So you want to tell the user that if it's saved, it's actually saved, or you failed the operation. Then the application can take the corrective action. So
with that setup, would that actually mean that, let's say I've got a SQL database that got like 60 gigs of data in it, how much RAM do I need on the boxes? Because if they all replicate the data and stuff, so how much RAM do I actually need to run it, or is the cache can have some kind of a priority and it's going to be, interacting with the database more dynamically rather than just pulling the whole thing into memory?
Actually, the cache doesn't make those decisions. You make them. Okay. So, the cache just gives you a mechanism to do so, and then you determine what data should go in the cache, how big that should be, and if you need to cache more of it, then you put more memory. So, for example, in our NCache product, we've got, as I said, the most common configuration is 16 gig. Now, 16 gig includes partition and the replica both. The 2 gig is usually spared for operating system and miscellaneous processes. So 14 gigs left, 7 gig each. But we've got customers that have 128 gig in each box. Now, when you have 128 gig, you need more processing power because the garbage collector is going to take a lot longer to collect 30 gig of data at once. So again, it depends on your need, how much data you need. And so sometimes it's better to add another box than to increase memory beyond a certain point. Because if you go beyond a certain point, then you're becoming like a database. Then you need a lot more processing power. So I would say up to about 128 gig is good. And anything above 128 gig, you should think about adding another box. Because these boxes are not very expensive. These are pretty cheap boxes. And, you don't lose any performance by having more boxes. Any questions on this? But this is a very core part of the architecture that I think you guys should understand if you do.
So this cache replication is within the cluster, right?
Yeah, within the cluster so far. Again, technically you could do this across the WAN, and some customers do it across the WAN, or some companies do it across the WAN. But there are other techniques that you can use for WAN replication. WAN replication is also an important aspect of a distributed cache that you should have. Because WAN has latency, and slowness means that the entire operation is slow. Especially if you had, let's say, a synchronous replication, and you had to go across the WAN. Then everything, and then let's say if you go from London to New York, it's about 30 to 40 millisecond round trip of one packet. So if you had one data center here, one in New York, every operation that you do is going to take 30 to 40 milliseconds. Imagine how slow that's going to be. Your application is going to just die. So there's no need to use cache in that case. But because again, you're used to sub-millisecond performance. If you can do 30,000 operations per second, that's definitely much less than 1 millisecond per operation, right?
Partitioning is all done by cache itself, right? I have no...
Most of the time. It doesn't, in case of big data, there's a benefit to you determining either what data is in what partition, or at least determining that all the relevant data is in the same partition. Because if you go back to the big data, what happens in big data is you've got, let's say, 20 servers. And every server is got some portion, 1/20th of the data. Let's say that you need to process 10 terabytes of data in a short time. So you will partition the data in each. So then what you want is your application and the data to be in the same process. Because if it's not in the same process, then the cost is fairly high, then you might as well just go to the disk. Although it's still faster than going to the disk, but it's not noticeably faster compared to if you could do it all in the same process. So there you would need extra features in the distributed cache to say, make sure that every partition has all the data that I have defined as related to each other is together. So then it doesn't matter where the data is. All that matters is it's all together. So if there's a customer and the customer's orders, and that's what you need to process, then every customer and their order should be in the same partition. But in an e-commerce or in a web application, you don't need that ability. So that's why the use cases that I'm talking about here, there's no need to determine which data is in which partition. Even in big data, there's no need to determine which data is in which partition. It's basically only keep all the related data in the same partition.
But what if I add the server to the cluster that is different in terms of specs, like memory and CPU from the others? Let's say you have larger memory.
That's something that is usually discouraged because, it just adds complexity for no reason. Memory is cheap. Let's just standardize it, because most of these caches are, I'll just say some of the caches do have the ability to know that how much memory is there, but most of them prefer that you keep same memory. In fact, many of them require that you use the same. They automatically assign partition size to be equal. So if it's not equal, then it just makes things okay. Then I talked about the client cache is another feature. So client cache is actually a cache. It's like a local cache that sits on your application or on your web server, and it can even be in proc. So it can be within your application process, but it's not a standalone cache. You could use a standalone ASP.NET Cache object, but the problem is then it's not synchronized. The client cache or the near cache is the beauty of this is that it is as local to you as the ASP.NET Cache object, but it is connected to the distributed cache. And again, many of the distributed caches provide this feature, and this client cache plugs in without any extra programming. You're programming as if you're talking to the distributed cache, and the client cache just intercepts things behind the scenes. And this is like a cache on top of a cache. So this cache was so that you don't have to go to the database as much. The client cache is so that you don't even have to go to the caching tier as much. And the client cache, all the client caches don't have the same data. It is based on the usage pattern of each client. So if one client wants customers from New York, that's what they'll have. One client has customers from London, that's what they'll have. So whatever they're fetching is what gets put into the client cache, and it gets put automatically. Now with the client cache, you have 3 copies of the data now: database, cache, tier, and the client cache. So you have to make sure that the data is kept fresh. So the synchronization part is important. You cannot do it in a synchronized way, in like a sync or async, because if every client cache was updated as part of the cache cluster, then the cache operation would become very slow. But there are other ways that caching products achieve this. Okay, so now let's come to Azure. So if you're developing application or if you're deploying it in Azure, and you want to use a distributed cache, or let's say you should use a distributed cache, what are your options? And I'm talking mainly from .NET perspective. So Microsoft gives you these 4 options on the left. One is the Azure Redis cache. Redis is an open source cache that Microsoft is using. It's a NoSQL key value store. The second is what they used to have originally, and that seems to be becoming less and less important. I could be wrong on this, but that's my impression, that the Azure Cache Service seems to become less and less important. And that is built on App Fabric, which is the Microsoft's own distributed cache. Then there's the Azure in-role cache, which is again built on App Fabric, and that's free. All the other options that don't say the word free are not free. So you pay for them. So you pay for the VM and you pay for the cache on top of it. And then the Memcached wrapper also uses App Fabric, and it's also built as a free option. The free means that you pay for the VM only, but you don't pay for the cache. On the right side, you've got there's NCache open source, which is free, and you can actually find it in the marketplace now. In fact, okay. And then there's NCache non-open source, let's say the enterprise and professional, which is not free, but and both of these provide Memcached wrappers. I'll talk about the Memcached wrapper in a bit. And there's also some third-party managed Memcached solutions which give you the Memcached interface, but they're managed. And then there's some third-party managed Redis solutions. So what are the different strategies for using a distributed cache in Azure? Strategy number one is in-role cache. That was the first strategy that Microsoft introduced, which is that if you have a web role or a worker role, the cache should just run on that same role. My impression is that the web and worker role seems to be becoming less popular or less mentioned, at least. And Microsoft is moving more and more towards the standard VM model. And so that was the first strategy. So then the cache could either be co-located, which means it's on the same role as your application, or it's dedicated, means that you have, let's say, a dedicated worker role, which is just for the cache. Strategy number two is that you use a managed cache service. That seems to be the most popular strategy from Microsoft's perspective. I'm going to explain what my opinion is on this strategy. But in the managed cache service, things are very simple for you because you don't do anything. You just ask, please give me a cache which is 30 gig. And they'll manage all the servers, they'll do everything. And you just get the API and you talk to it. The third is the cache virtual machines, that you actually get the cache as a virtual machine, which is part of your service, your deployment. And in this, so now if you see the options in each strategy, so in-role cache, you've got the Azure in-role cache that we mentioned, and you can use the NCache also, either the open source or the Enterprise Pro. In the managed cache service, you've got the Azure Redis cache is also a cache service. The Azure Cache Service, of course, that name itself indicates, and that there are some third-party managed Memcache services and the third-party managed Redis services. And the cache virtual machines is the only option that you have from what is there on Azure is NCache. You could take your own, let's say, App Fabric or Memcached and install it yourself on these virtual machines. So technically, you can deploy a distributed cache on a virtual machine. Any on-premise distributed cache can be deployed on a virtual machine. But whatever Microsoft is providing, they're not providing anything on the virtual machine. The only thing that is available from that perspective is NCache. And I'll explain why I think virtual machine is the better strategy. And I'm not saying NCache. I'm saying virtual machine, any distributed cache, is a better strategy because managed cache service, although it's easier for you because you don't do anything, it's also very limiting. For example, the entire cache cluster is a black box for you. So you have no access. You just make the API calls, and you get some basic monitoring on it. You cannot run any server-side code, so no read-through, write-through, cache loader, none of that. And most of these have limited number of servers. So, for example, the Azure Redis, when you try to go in this, their default is either 1 or 2 servers. What if you want 4 or 5 servers? So the flexibility is not there as much. And so my recommendation is to deploy a distributed cache on a virtual machine. Go ahead.
Do you use different clients? For instance, the VM Redis or the managed Redis is a different VM, and from the DevOps configuration, is any different?
Actually, what Microsoft gives you, Redis is only available as a managed cache service from them.
Right.
And so is the Azure cache. But as I said, the only way you can have Redis on a virtual machine is to do it yourself.
Yeah. But from the configuration, it will be different, right?
Yeah, of course. So it'll be just like you're doing it on-premise. You have the VM, and you install the distributed cache on it, and you configure it and do all that stuff. Did I answer your question?
Sort of. My question is like on the web app, right? I have a connection string, let's say, to
Right.
the database or to the cache
Mm-hmm.
cluster.
Right.
So would that connection string be any different if I point my web app to the managed? or
No.
to my own? So
No,
it's-
no. From a client application perspective, it's the same API.
It's the same API. Right?
Yeah, same API. What is different is that you cannot have any server-side code, which is an important component of this. And there are also a lot of other features. I mean, as I mentioned, the application data caching means there are 2 copies of the data. One in the database, one in the cache. Well, there are some features where the cache can synchronize itself from the database. You cannot do that unless you have server-side code or something of that nature. So you need more access, more control on the cache, and that's what the VM does. Okay, let me quick.
Sorry,
Go ahead.
server-side code. Would that mean that you can actually put some procedure to work on the data, the cache, or is that not something that?
For example, yeah, very good question. So let's say that you want to do that big data analytics. So that analytics is your code actually that needs to be deployed to every cache instance, every partition, and run on that partition, and then process things locally. You can't do that with a managed cache service because you don't have control over that code.
So it's almost as like moving the let's say SQL search procedure into kind of more managed work.
Yeah.
When you got all the data, in your RAM, it's faster and you can do all the other stuff.
Exactly. I mean, RAM is much faster than any disk. Even SSD is much slower than RAM. And
So the manager is probably just for the sessions, right? For the sessions only.
even for the sessions, you need to have more control. As I said, it started because Memcached was it didn't have any server-side capabilities. So the only thing it had was the client API. So it became as a common practice to use Memcached. Amazon started an Elasticache, which is a Memcached based cache as a managed cache service, and that caught on as a strategy, and that is what Microsoft has done too. But I think Microsoft will probably change their mind down the road and will give you cache VMs. I mean, we've already provided cache VMs in Azure as part of the Azure Marketplace, both open source and paid, because we strongly believe that gives you a lot more control than the cache service. Because the other part is that the cache needs to be as close to your application as possible. That 30,000, 50,000 performance that I was mentioning will not happen if you have to go through multiple hops. And if you go to a managed cache service, you are most likely going through endpoints, and So the performance is another aspect that I didn't even mention here. If you do everything virtual machine, everything's within the same subnet. So it's very close to your application. And the whole reason you're doing cache is so you can optimize performance. Okay, so let me, I'm just going to quickly show you an example of how distributed cache works. I'm going to use NCache, but that is by no means saying that that's what you should use. Make up your mind about what is the best option. So I'm going to create a 2-node cache cluster. You can do it either through a command line or through a graphical tool. So if you did it through a command line, you would use something like this. You would do a create cache and those tools. I'm not going to use the command line. I don't want to take that much time right now on this part because there's a lot of other material that I want to cover. So I'm going to use a graphical tool to create the cache. And again, this VM is something that you would be able to create by going and taking it, because if this were NCache, because it's a VM image, so you just create an instance of that image in Azure. Here's my Azure console, and I got 3 VMs running, 2 for cache nodes and 1 for the client, cache client. So I'm going to come here and say create a new cache. I'll name my cache demo cache. I'll choose a caching topology, partition replica is what I'll choose. I'll keep an async replication, which is, and this is .4. This is .5. Okay, so I'm gonna choose my first cache node as 10.0.0.4. Second one is 10.0.0.5. Oops. Let me just go ahead and remove this. So I've just created a 2-node cache cluster. I'm going to go ahead and add a client to it, 10.0.0.6. I think that's what it's going to be, if I'm not mistaken. And if I click on this, I'll see all the properties. I will go ahead and say start the cache on both the nodes. So the cache is a server process. So every server has its own cache process. Just like a database, except that these processes are talking to each other. So they form a cluster. So I'm going to go ahead and say statistics here. And now I'm going to go ahead and run a test program just to do some activity. So this could be your application, making the cache calls. There's a stress test tool that comes with NCache. So now this program is just making, it's in a loop. It's just making get, insert, add, insert, get, add, insert, get. It just keep on doing. So it's, as you can see, it's doing about 700 requests per second per box. So when I said 30,000, it doesn't mean it's going to happen from one client, because one client doesn't have the ability to push that much. So you need to add more clients. So one of the things that whichever cache you use, they should give you some sort of a stress testing tool so that you can actually put the stress within your own environment. So it's always better to test things in your own environment. And your own application, it might take a lot longer for you to test through your own application, because you have to go through, if it's a web application, you have to use some stress test tools that'll put the stress on the web, and then that calls the cache and all, which you'll do eventually. But initially, just to get a feel of things, it's a lot easier if you can do it with the tools that are provided. Otherwise, you'll have to write your own programs. So I'm, for example, going to use one more instance of this tool, one more instance, and it's going to, there, see, it increased the capacity. So if I keep adding more instances, if I have multiple client boxes, you'll see that this is going to go up and up and up. And then it's going to reach a stage where I pretty much maxed out 2 nodes. So I add a 3rd node. Then I will be able to go up and up and up. Then I'll max out, then I'll add a 4th node. So that's how you scale. Which is something that you don't have with a relational database. So, I just wanted you to get a feel of what a cache looks like. Now, let's come back to those 3 common use cases. Now we'll talk about actual, from a developer perspective. Up until now, we've been talking architecture, deployment, and more IT stuff. Now we're going to talk more dev stuff. And we've got another 22 minutes left. Okay, so we've talked about these 3 use cases. Let's see what they are. So application data caching. A typical code would look like you're trying to load a customer from a database. You will first check it in the cache. If the cache has it, you've got the object. So no need to go to the database. If customer is null, that means cache doesn't have it. Then you go and you call whatever your persistence code is, and it gives you back the customer object. Whatever that code is, that's your. So then you want to just add it to the cache. Why do you want to add it? So the next time you call this method, you will find it in the cache. So then you won't have to go to the database. This technique is where the application is directly going to the database and then getting the data and putting it in the cache. So the next time it will find it in the cache. So the cache is on the side and your application is talking to the database. The other strategy is where the application always talks to the cache and there's a server-side code. So then the application, when application does this, cache customer equals cache key, this talks to the there. So this talks to the cache. The cache calls your read-through handler, and the read-through handler goes to your database, gets the customer, then gives it back to the cache. The cache puts it in the cache and then gives it back to the client. So from a developer's perspective, this call never returns null unless the database doesn't have it either. So that's when you would have the server-side code. Now, the nice thing about the server-side code, if you can do it through the read-through, is that it simplifies your development. Most people don't have to write database code. They'll just, cache becomes your main data interface, which is a much simpler interface than writing all those ADO.NET code for everybody. And then having everybody use it and maintain it instead of keeping it in one place. So the cache becomes a central repository of all the persistence code if you do the read-through right through.
What's going to happen when your data is larger than your cache, and your data grows so much that your
Actually, that's always the case. I mean, the cache, you don't cache more than 10-15% of your database normally. It's a moving window. So that's where the cache has features like evictions. I didn't mention them here. So the cache, because the cache works in memory, it has this feature where the data, either you will expire the data yourself, so the cache should have a feature called expiration. So that you say, okay, I don't think I need this data for more than 10 minutes. So after 10 minutes, the data is gone. Or expiration could be sliding, which means that you're not accessing that data item anymore. So after inactivity, the data is removed. Sessions are removed that way. So if an ASP.NET session object is put in the cache, when the user logs out, that session is no longer being accessed. So then after 20 minutes, it's going to be expired. That's one way to remove it. Second is that you actually specify a maximum cache size and say, I don't want you to consume more than 7 gig per partition. So when the data reaches that size, then you specify an algorithm, let's say a least recently used algorithm. So there are eviction algorithms that a cache should support, and that's something that I didn't mention here, which is that it will evict 10% of the cache when it reaches that threshold. Let's say, and the reason it needs to do that is because cache will almost never be as big as the database, and it cannot be because the data is much larger. So here's a typical API, and although this is the NCache API, but it looks pretty much the same in most caches. At least that much of it looks pretty much the same. There are differences in more advanced features, but the basic cache looks something like this. So you connect to the cache, you get a cache handle. That cache handle is what you use everywhere. You do a get, contains, add, insert, insert, remove. I mentioned that in case of application data caching, the data exists in two places. So a good distributed cache should have the following features. First, it should keep the data fresh, and it can do so through expirations, through synchronization with the database, with the relational database. For example, there's a feature in SQL Server called SQL dependency. I don't know if any one of you have used it. A cache, a .NET cache at least, should use it. And the same way there's an Oracle dependency and so on and so forth. So that whenever you cache something, if you think that data is going to be updated in the database through a third-party tool or through some ad hoc querying tool, because if your application is the only entity that is updating the data, then your application can also update the cache, right? There's no problem. But in most cases, especially in larger companies, third-party applications or tools also update the data. When that happens, you want the cache to be able to synchronize. So the synchronization could either be event-driven, which is what the SQL dependency is, or it could be based on polling, but there are a bunch of strategies. But either way, the cache needs to know that the data exists in two places, and it needs to provide you features to synchronize. This is something, for example, if you did this with the managed cache service, you wouldn't be able to do this easily. But you can do it from the VM. And this synchronization could be with the relational database or with any non-relational. It could be mainframe. Because this is your code that actually goes and checks if the data has changed. The second is, most of the time you are probably dealing with a relational database, where there are relationships among different data items. So there's a customer has multiple orders, and order has multiple order items. So if you're removing a customer from the cache, you might be deleting it from the database, for all you know. So it makes sense to then be able to tell the cache, well, if a customer is removed from the cache, remove all of its corresponding orders that are in the cache. So the cache no longer has incorrect data, because the last thing you want is the cache to have old data. So you remove the customer, but all of the orders are still there. Maybe customer order is not a good example, because you don't usually delete a customer, but I mean, you get my point that if you have one to many and you delete the one side from the cache, the many side should also go away from the cache at least. Similarly, your application is used to searching data from the database. Now that you're putting it in the cache, key value is not sufficient. You want to be able to search and say, give me all the customers where the customer.city equals London. So, or you want to be able to group things. Now, many of these features are provided by multiple caches, but again, I just want you to know that you need to be able to do this. And then if you're doing searching, then the cache needs to support indexing, because without indexing, the search is going to be extremely slow. Then there's a read-through, write-through that we talked about already. That is your code. There's also a cache loader that many caches support, which when you start the cache, it pre-populates the cache with your desired data. So again, these are things that are making your cache more friendly, more capable, and less headache for you. Otherwise, you'll have to do all of this through your own code. If your cache is being used by both .NET and Java applications or multiple languages, then the cache should ideally support portable data types, which is either binary or JSON. JSON has some cost associated with it because you have to transform it from an object form to a JSON. But if you've got only .NET and Java, then many of the caches have a portable data type binary format, which is super fast. Then there's locking, there's bulk operations, async operations, streaming API. So those are all the things that application data caching features would need. We've talked about the API part. So there are 3 different environments from where you can actually plug in. Go ahead.
So when you said locking, so what sort of...
Locking would be, let's say that you want to update multiple cached items as one atomic operation. So you want to acquire the lock on them before you update, so that nobody else can either read or write the older copy.
So this means you're making synchronous?
It is not synchronous. I mean, it is sort of halfway towards a distributed transaction with a rollback. It does not have a built-in rollback because cache doesn't really need that complexity because you've already updated the database. But you want at times the ability to say, okay, now that I've fetched this object, don't let anybody else update it. And I'll give you an example. ASP.NET Session. Once your page starts executing, it fetches the session from the cache. While the page is executing, it doesn't want anybody else to fetch that same session. So when it is done and the response is being sent back to the user, the session is saved and unlocked. So there are lots of use cases of that nature where you want to lock something so that nobody else can read it. So now you did a read and lock and then an update and unlock. And there are also other cases. If you have an entity framework application, unfortunately, currently Entity Framework does not provide an entity level cache plugin like Hibernate does. And Hibernate is as you probably know, is an open source equivalent of Entity Framework. Although Entity Framework has become very popular in .NET because Microsoft is pushing it, and also it's pretty good actually. But those are the 2 leading object relational mapping engines that .NET developers use. And if you're using an OR mapping engine, you can plug in a cache without any programming. It's always nice to be able to plug in, right? So there's no programming needed. Of course, if you plug in, if you do API programming, you get much more control. Sometimes you want to start with plug-in and then see how it's going and then put the development effort to actually make the API calls. So the entity framework, even though there's not an entity level model, some of the caches have implemented ADO.NET, a custom ADO.NET provider, which has built-in caching, but that is at the SQL query level, which is not as powerful as at the entity level, but still it's better than not having it. Another thing that is common is there, because Memcached became very popular, especially on the Unix and PHP and Java side, and also .NET. There are a lot of people who use it. But Memcached has high availability issues. It does not do replication. It does not have dynamic cluster. It doesn't even have a cluster. So people had made the investment into Memcached, but they wanted to have a more reliable Memcached equivalent, or with the same, let's say Memcached compliant cache. So many of the leading caches that were a lot more powerful than Memcached started providing a protocol level support of Memcached. So NCache does it. App Fabric, Microsoft uses App Fabric to do so, and there are also third party like Amazon had the Elasticache. So the protocol server exists for that reason. So if you already have programmed Memcached, if you haven't programmed Memcached, my recommendation is don't go with Memcached API, because it's very, very basic. You can't really gain the benefit. And there are much better alternatives. Open source, even open source, you've got a lot better alternatives, in my opinion. Again, I don't want to offend anybody who's Memcached enthusiast. The second use case was ASP.NET specific data caching, and that I mentioned there is session state, view state, and output cache. I already showed you that the session state is another major bottleneck. You wouldn't believe how many ASP.NET applications that are high traffic are having issues with session storage. Microsoft in Azure gives you only the SQL database as the option. SQL or any relational database, the sessions are stored as blobs in SQL, and SQL, like any relational database, wasn't designed for blob storage. It was for structured data. So a better alternative would be to have a NoSQL alternative or in-memory. So in-memory is faster than NoSQL. So that's another use case where a lot of people use an in-memory distributed cache to store sessions. And again, there's a SSP, session state provider architecture, which just plugs in. There's no programming. You just modify your web.config. There's a session state tag that you specify. Make sure your timeout is this, and your sessions are stored. So very easy to use, and an excellent way to start using an in-memory distributed cache. Excellent way. And here's basically it's that same caching tier is now storing the sessions. So the sessions are not being stored in any of the permanent data stores. Although they could be stored in NoSQL, which would be better than relational. But as I said, an in-memory distributed cache is also open source. It's even if it's not open source, it's much faster and much more appropriate, in my opinion, for sessions. View state is another one. For those of you who don't know what view state is, if you're not developing with MVC framework in ASP.NET, most likely you have a view state. View state is an encoded string, looks like this, right here. This string is sent, and it could be hundreds of kilobytes. This string contains some state information, gets sent to the browser. The browser just keeps it and sends it back, does nothing with it. And this can consume a lot of bandwidth and slow down. I've seen companies who had hundreds of kilobytes of view state, and as soon as they cached it, immediately performance went up many times. So the response time increases dramatically, or response time, it becomes faster dramatically. And second, bandwidth is not free. So because bandwidth is not free, if you multiply those hundreds of kilobytes per request times millions of requests that you have to service every day, it can become a lot of money. So you're saving money, and it's like win-win. Can't go wrong with this one. And it's also a plugin. Many of the caching vendors who support this do this through a page adapter. So they have a custom page adapter implemented that you just need to plug in. So there's no programming on your part. So there's a .browser file that they will give you, which contain this information. They have a custom page adapter implemented, and then you register that in your web.config. Pretty straightforward. And the view state, when you cache it in a distributed cache, it is immediately available in the entire load balanced web farm. So if the original request started from server 1, now it goes to server 5, it's going to pick up the same view state as compared to each server having its own view state. So that's the benefit. I've talked about this already. Page output is another benefit. Your output may not change, but the page still gets executed. When a page gets executed, it consumes CPU, memory, makes database calls. Actually, most importantly, it makes database calls, which is the real bottleneck. So if you know that the output is not changing, not every time, let's say, unless some parameter changes, the output is not going to change. Let's say that you knew that. Then for that parameter at least, you can cache the page output and then use it. There's an ASP.NET output cache framework already provided by Microsoft. Plug in distributed cache in place of it so that it's available across multiple servers. It's much faster, consumes less resources to just fetch the output than to re-execute the page. The third use case, last but not least, is the runtime data sharing. That I said most people don't realize that a distributed cache should be used for this. Now, I'm not talking about sharing data across the WAN. I'm not talking about a distributed from that perspective. I'm talking about multi-server environment within a data center, which is what most of the runtime data sharing is all about. You've got multiple applications or the same multiple instances of the same application who are or that need to share data with each other. Traditionally, they used database polling. So one application instance stored data in the database, the other one kept looking for it. The least effective way to do it. Then came database events, that SQL dependency type of a thing, or SQL notifications, same way Oracle notifications. So these applications registered for those events, and the database fired those events. Much better than polling, but still, the problem is it's not scalable. These events have quite high overhead in the database. So if you have a high traffic environment, again, I'm talking from that perspective. If you only have 10 users or 50 users or a couple of hundred users, then whatever strategy you pick is going to work. But if you have, as I said, 5,000, 10,000, 50,000, 500,000 users, millions of users that come to your website or your application, then you really need to squeeze the juice from every way you can. So the message queues were the third way. They're definitely better than the database events, but they're not data-oriented, so they're message-oriented. Secondly, they're also not scalable. And sometimes you need to share data based on messages. Sometimes you need to share data based on data. That, okay, tell me if a new customer is added. Tell me if this one customer changes, or whatever. Or tell me if the price of this product changes. So the message queues have the same issue. The benefit of message queues is that they're good at distributed, like across the WAN stuff. But within the same data center, they don't really add that much value over a distributed cache. When you have an in-memory distributed cache used for runtime data sharing, you have a cluster, which is a scalable cluster. That's what I meant. The message queues don't give you this. And it's in-memory as compared to persisted, and you can share data across through events. So some of the things that an in-memory distributed cache provides for runtime data sharing is portable. The first thing is portable data types, because anytime you're sharing data, most likely you will have .NET and Java both, or maybe even other languages. So it should either be binary if it's .NET and Java only, because that's faster than JSON, or JSON if you have more than .NET and Java. So if you store data in that format, then you can share it with other language programs. Then there are some data-focused events, which, as I mentioned, the message queues don't provide, which is item level. So you can say, if this item changes, notify me. There's also a feature that some of the distributed caches provide called continuous query, which is, it's like a SQL dependency, actually, but it's on a cache. You specify a SQL type of a criteria. So, for example, you'll say, select customers where customer.city equals London. So that becomes your data set. Then any customer with city equals London, if it is added, updated, or removed from the cache, you will be notified. So it's a data-focused events that based on which you could take action. Now, if you start to think about the types of applications you're doing, you'll see there are a lot of applications. There's a lot of use of this feature that you can take advantage of. And there's also cache level event. Anything that is added or updated to the entire cache, notify me. Then there are some message-based events like message queue. But again, the benefit is that the cache is much more scalable and faster. So there's some custom events which are application specific. So if I send you this one event, you can take action, and you're looking only for that event. There's some topics. So a topic is like a custom event. So you say, if I send an event, I'll fire an event to this topic. That topic event could get broadcasted to all the people who are interested in that topic. So if there are 5 different applications that were interested in that topic, they would get that event. Whereas a queue, if there were 5 people interested in a topic, only the first one would get the event, whichever one picked it up. So topic is broadcast, queue is like a one-to-one. So those are the 3 types of data. I think we passed the time. And then there's some code examples on how you can do this. I'm going to actually just... I'm 3 minutes over.
Sorry, said you can run this server level server-side caching on the caching, like for example NCache. On the cache, is there any pluggable wrappers that you can use, like for doing any extra logic?
Yeah, so all the server-side code are interfaces that you implement. So there is an interface for read-through, interface for write-through, interface for cache loader, interface for that custom database synchronization. So all these are interfaces that these caches provide. And you implement that interface and you register your code with the cache. And that code gets propagated to all the cache servers. And again, keep in mind, that dynamicness now also comes into this picture. If you had deployed your assembly to a cache server, now you want to spin a new cache server and add it at runtime, you want all that code available there too. So the cache should be able to take care of all of that for you. So the high availability is when you dig deeper, it's a very complex thing. And that's why not everybody provides it. Any other questions? Thank you for your patience with me, and I hope this was informative. And please go and take a look at this as your option. I think if you have high traffic, high transaction application, you should definitely use a distributed cache. Thank you.